Okay. Sorry for the delay. But okay, we'll start the session. Okay. This is our eighth session for the Nanomaterials and Their Properties course. I'll upload the into the YouTube anyways. Yes. That's it. I also don't have access to the touchpad since I'm traveling. Prepared the slides already. So we talked about how different methods. So when we have mechanical alloying or milling, where you have ball mill. Let's choose the mouse, please. So here we have a rotating drum in which we have our uh, two nanoparticles of two components, and you have your ceramic or steel balls. As this drum is rotating, these balls rise along with the drum, and they'll fall from this point, impacting the blender, the wall of the drum. And if there's a nanoparticle trapped in between, the powder trapped in between, that will get subjected to high pressure and temperature. That will cause reaction to take place, solid state reaction to take place locally. There are high energy ball mills where they use planetary ball mills. Uh, I discussed them in the last class. Where if you see at the intersection of these, where the collision happens, there's extreme deformation in the particle and the cold welding happens. So here's they've shown two ceramic balls colliding with each other. So if there is already there are lots of ceramic balls inside this drum. Some will be at the bottom. The top ones will collide with them. That's what between them you'll get the plastic deformation. So, but if your material is very ductile, this ball milling doesn't really work. It will just have plastic deformation in the particles. You want to actually break them into smaller and smaller chunks to get nanomaterials. Then you use cryogenic temperatures. So you cool down the sample, making it more brittle. Okay. For brittle materials, this method is okay. Then you have consolidation by sintering. This is hot uh, isopressing. So HIP, hot isopress. So you have your heating die and your powder in between. You apply pressure from both ends. The combination of heat and pressure causes the powder to center. This is a depiction of the sintering process. You have two particles sitting together, and the pressure and temperature both increase the diffusion, causing a neck formation, and eventually you get a complete particle. So it will become a completely single piece with definitely a grain boundaries in between. So sometimes you even don't have heating elements. You can use graphite dyes, and your powder is pressed in between that graphite dye, and you pass current through it, current I. And as the current passes through that graphite, you get I square R heating. That will be the power required, and that heating will cause the powder to fuse along with the pressure applied. Next, we have micro machining, where again machining you're going. These are all top-down approaches. So in machining, you have a bigger workpiece, and you use cutting tools to break them into smaller pieces. Examples are micro machine. Micro machining this is how much particle size, feature size you can get. So micro machining you can get down to 10 micrometers. You have EDM, which is electro discharge machining, where you have uh, a current carrying uh, high voltage current wire, which as it comes into contact with the working workpiece, it slowly erodes the surface near the wires from sparks, a lot of sparks. So that cuts the sample. Again, you get around 10 micron um, feature size or tolerance. You have electron beam machining, where you use electron beam to cut down to locally evaporate or butter the material to remove it and cut the workpiece into the shape you want. You can get better accuracy, more tolerance, 5 microns. Femtosecond laser machining, again, you have laser pulses, femtosecond range. You can get to even more lower tolerances. And you have focused ion beams, where you have high energy ions which are bombarded on the surface, which does the machining, cutting the piece. Lithography, again, this is a top-down method. So here you have your silicon wafer. On top is your silicon oxide. Okay. You coat it with the photoresist. So this uh, light grayish creamy color layer, this is your photoresist. And you apply a mask on top of it. This mask blocks the UV light falling on the photoresist. So wherever the UV light falls, this is, I think, positive photoresist. So wherever the light falls, no, this is the negative photoresist. Wherever the light falls, that area gets removed. Actually, not get removed, so that becomes susceptible to etching. So here in this step, step A, you just bombard it with UV light. In step B, you dissolve the exposed resist in some acid, maybe HCl. So only the exposed part gets removed. Okay. That remaining part is there. Then you used some other acid or some other chemical to remove the silicon oxide layer, and then you this olive color layer. So this photoresist prevents the etching of the silicon oxide layer, and the acid only able to attack it from the sides. So you get these features, and then finally you remove the remaining resist using some other solvent. And yeah, then again you can use etching to get etch the underlying silicon, which again is the silicon oxide layer is protecting silicon, and as exposed silicon, you can etch it away. So here, actually, the diagram shows what happens if you do overexposure and underexposure. If you have underexposure, you'll get features like this. This is your photoresist, and you won't get perfect sharp edges. However, if you keep it for too long inside acid, you'll get over etching, where the acid starts attacking from the side and etches your maybe silicon oxide, in this case, from beneath the photoresist. Uh, then you have the typical stress strain plot. So okay, so this is your typical stress strain plot. So what happens in stress strain plot? You have a dog bone shaped sample. You apply some force at the top and grab the sample from the top and the bottom. You clamp it and you apply tensile strain. You stretch the sample. You have your width of the neck in the thinnest region. This is your neck width. This is your L naught is your initial length, and as you elongate it, your new length is L dash. And so, if you know the width and the thickness, you can apply the stress. Stress is just the force per unit area. So, if you know the width and the thickness, you have the cross-sectional area. So that's the stress, vertical axis, and the strain is just the new L dash minus L naught divided by L naught. How much your length is increasing? That's the strain. So what will happen is initially you have your elastic region. In elastic region, whatever stress you apply, whatever strain you impart on the sample, as soon as you remove that stress, it will come back to the original state. It follows this linear path. Okay. However, once it reaches the plastic region, so your stress is above this uh, deformation limit. Let's call it Y. Above this stress, what will happen? Once you remove the stress, there is permanent deformation inside the sample. So this yield strength, this is called yield strength, point where plastic deformation starts to happen. So what we usually take this as a 0.2% offset. So once you remove the strain, it reaches the 0.2% of the original value. That's the yield strength. That's the yield strength. Yeah. So at whatever point in the plastic region, this is plastic region, whatever point you remove the stress, it will come back to uh, some, not the original length, but yeah, it will shrink back to some length. And the line, the slope of this path taken is same as this initial slope actually. The slope never changes, just there's some residual stress strain remaining inside the sample once you remove the load. So once it reaches your maximum load, your tensile strength, then your neck starts forming and eventually your sample breaks, which is your fracture point. So your tensile strength is the maximum load the sample can take. At that point, this point onward, you see a neck formation going on. So as the area is decreasing, since the force is same, the stress inside this neck region increases, keeps on increasing, and even if you decrease the load, still there is plastic deformation taking place, and the sample will start to break. That's because the narrowing happening beyond this ES point. So yeah, your force is remaining constant. Since your area is decreasing, your strain is increasing after the maximum load. So now if you plot the true stress strain plot, so now since here your the stress, so this stress, uh, how do you calculate the stress? This is the total force divided by the area where you're clamping the sample. Okay, this is not the area where at the thinnest point of the sample, not the area of the neck. If you divide the force with the area of the neck, force divided by the area of the neck, then you get your true strain, true stress. True stress and your that value of that strain is true strain. When you plot the true stress strain plot on a log scale, you get a linear relationship, and the moment the neck starts to form, at that point you see change in that slope. Okay? That's how you can identify where the neck starts to form. And the slope n is your strain hardening exponent. So this is the relationship sigma is equals to k not epsilon to the power n. If you take the log of this, the n comes out in the slope. So you get the slope of this log sigma log. Okay. Flow curve. So because it is a straight line on a log plane, this is the relationship in the plastic region. Sigma is equals to k epsilon to the power n. K is your strength coefficient and n is your hardening exponent. Here I've just taken the log. Log k is your intercept, slope, and n is your slope. Plot. And you can have different type of stress strain plots. So for brittle material, you don't get plastic deformation at all. And after a yield strength, that, that will breaks at that point. You can also have elastic material where material is very ductile. So this straight line linear region is very small or non-existent, and you get very large strains. But yeah, the tensile strength. Usually for brittle material, they have very high yield strength, but not they don't really expand that much. Another property is hardness. So that's defined as resistance to permanent indentation. A good hardness generally means material is resistant to scratch or wear. So most tooling, so the tool, whenever most of the tools you use cut the sample, your working metal, working piece. So your tool must be harder or less, more wear resistant than the working piece in order to get the cut. You cannot cut rubber to cut a rock. You need to use harder material. You cannot use steel to cut diamonds. You can use diamond to cut diamond, but that's or steel to cut steel. And then there are different methods. So there's Brinell method, Brinell hardness or Wicker hardness. That depends on the indent diameter of the indenter. Patient left. We have diameter of the dent, the indenter, DD. Your dent diameter, B. And you get your HP, which is your Brinell hardness formula. This is the force applied. The diameter of the indenter, indent on the surface. You can convert between different hardness scales using some conversion factors. They depend on the material too. Then you have shear stress. Shear stress is just tensile or compressive stress. The stress is applied clearly along the same direction. The tensile, both these ends are pulled apart, and then compression, these two ends are compacted together. However, in shear stress, force is applied on the surfaces parallelly. So on this two surfaces, force on the top surface, force is toward the right and left. The shear stress is defined as tau, which is force divided by area. And your shear strain is defined as uh, delta x deviation divided by your h. Or this will be equal to the tan theta. Tan of this theta angle. Oh. Value change in tan theta. Initial tan theta will be just height divided by base, and then it will deform by delta x. Delta x by h is your. Then you have viscoelastic behavior. So viscoelastic behavior is where material, even under constant stress and temperature, over time the stress strain plot changes. So you're maintaining the same stress level, but your strain is changing. So in normal material, if you have some stress applied and you stop at that point, the strain that the strain that remains in the sample. However, in viscoelastic material, so on the right, you have elastic behavior and viscoelastic behavior. Elastic behavior, and this is your stress applied. Okay. So you apply some stress for some time, and you get the strain which is maintained over that time and doesn't change. However, in viscoelastic material, you apply some stress and you fix that stress for some time. However, the strain is increasing. So slowly the sample is elongating, maintaining even though you're maintaining the same stress. Okay, so that's viscoelastic. So it's combination of viscosity and elasticity. So slowly these polymer chains are sliding on top of each other. Your sample is increasing. Then you have different point defects in your material. So in point defect, interstitial defect is you can have different interstitial defect. So uh, this you can have either tetrahedral or octahedral. So whenever an extra atom comes into your lattice, so if the extra atom sits in the interstitial, the tetrahedral void, that's the tetrahedral defect, and the new atom sits in the octahedral void. The octahedral defect. You can have substitution defect where one atom is replaced by another atom, and then you can have vacancy defect where one atom is completely missing. Okay. So this is just an example of different tetrahedral and octahedral voids. This will structure FCC, BCC, FCP. And you have your line defect where you can see uh, this plane is getting, this plane is not running throughout the sample. This is a line defect. You can have edge defects where, again, this is similar to the line defect, 3D. This one row of atom is incomplete, so there is no atoms corresponding here. You can have screw dislocations. This is the edge dislocation, and this is the screw dislocation. Both these, so edge dislocation is a very, uh, all these dislocation methods are how plastic deformation happens in your sample. So you apply this strain, slowly these dislocations migrate toward uh, one edge, one side, and that causes the plastic deformation. That's an example. Dislocation pile up. Here's the example. So if you apply stress over in the top, shear stress on the sample, what will happen is slowly these uh, dislocations will start piling up against the grain boundary. So in case of grain, so here you can see these dislocations as they encounter a grain boundary. Since the grain boundary is at a different angle than the slip plane, so the plane is vertical, the obstacle is at an angle. So what will happen is this dislocation wants to move across this grain boundary, but uh, they are stopped at the grain boundary. So more and more dislocations come up and starts piling up at the grain boundary. This causes some generation of back stress, and this is a reaction of a resolved shear stress. Okay. So as you can see at the grain boundary, there is the dislocation density is increasing, causing back stress. So this is a method of providing increasing your strength of your material by preventing dislocation movement. So you can, if you have smaller grains, so there will be a lot more grain boundaries, and yeah, and there will be a lot more grain boundaries, and there will be more dislocation piling pile up that will reduce the plastic deformation in your sample. There are other methods too, like adding precipitates inside the grain, which again hinder the movement of this dislocation. This dislocation is what is causing the plastic deformation. So whatever you do to of their motion, during boundary or the precipitates, that will increase the yield strength of the material. So this is a famous Hall patch equation, which tells you how the grain size affects the yield strength of the sample. You see yield strength of single crystal. As you decrease the particle size, your yield strength increases. D, D decreases. You can see hardness. Hardness again is just how much it material resists plastic deformation. As you're decreasing the grain size, your hardness. So if you see, so this D is the particle size, and then there's dislocation spacing, right? So there's dislocations pile up, you have some spacing, equilibrium spacing in between these dislocations. When the spacing size becomes similar to the actually when the particle size becomes similar to this dislocation spacing, that's when this Hall patch uh, what we call Hall patch equation breaks down. Since now there's no dislocation pile up. As soon as a dislocation is formed, it reaches, there's no more like there cannot exist more than two dislocation in the sample in your grain set. So what will happen is if you generate more dislocations, one dislocation will move across. So the dislocation piling won't happen. The cell patch equation. There's some practice questions now. During mechanical or ball milling, nanocrystallites form at room temperature, elevated temperature, cryogenic temperature, or all of them. So for if you have your the sample is very brittle, even at room temperature or elevated temperature, you can get nanocrystalline nanopowder. However, if your sample is very ductile, then you need cryogenic temperature to reduce the ductility of the sample. Okay, so all of this depending on what type of material it is. During sintering, the coalescence of the powder particle occur due to both pressure and temperature. So you can think of as the pressure is increasing, the vapor pressure is increasing surface. So less number of particle the atoms from the surface escape to the surrounding atmosphere and will diffuse, right? Want to diffuse to the other sides, lower energy sides. Temperature itself, as you know, temperature increases the diffusion. Yeah, that increases benefits of sintering. Whatever method, whatever process increases diffusion will benefit. Composition doesn't really change diffusion. Top-down synthesis of nanomaterial is uh, in top-down material you have larger sample, your workpiece, which is broken down into nanomaterial or smaller pieces. It's a destructive method since you cannot go back to your larger sample just by placing them together. And it's really energy intensive since you are breaking lots of bond at the surface. You're creating a lot of new surfaces, right? As you're breaking it down into smaller pieces. If you remember, nanomaterials have very large surface to volume ratio. And all the energy you are providing goes into creation of these new surfaces. It's a really very energetic and intensive technique. Even like uh, when you see companies digging out large rocks from the ground and breaking down into smaller pieces, gravels for filling it in the roads or making buildings out of them. Almost 80% of the energy, 60 to I think 80% energy just goes inside in of the entire process goes into breaking the rocks into smaller pieces. The stress strain relationship for a perfect elastic material K is constant. So sigma is equals to the perfect elastic. You never enter the elastic region. So the stress and the stress strain plot is linear. That's what perfect elastic material is. So your ceramics and all, they're very brittle. Go into elastic region, always stay in the elastic region. So in that region, the stress strain follows linear straight line in relationship. Versus straight time. K is your Young's modulus. The point of change of slope at the upper end of the linear region of the stress strain curve. So at the end of your linear region, where the plastic region starts, is your yield point. Ultimate tensile strength is your maximum load, PS. Fracture point is your where the sample breaks. Through stresses, yield strength is the point. Brinell hardness we saw uses a spherical indenter. So the relationship between the stress and the strain for the plastic region follows what curve? So you saw the two stress strain plot, low curve in the plastic region. Sigma follows this exponential relationship. K times epsilon to power n. Okay. Stress is equals to K times K into the power. One. No, sorry, n. Strain hardening. Relationship between dislocation line L and the Berger vector for screw dislocation. For screw dislocation, B and L are parallel. Have this shown it in the figure? B is your Berger vector, and D is your dislocation line. In edge dislocation, both are parallel, whereas in screw dislocation, Berger vector is vertical, and your D dislocation line is along the surface in the plane of the cylinder. Vertical. Material which involves plane time which depends on time and temperature. That was your viscoelastic material. So if you're maintaining a constant stress over time, your strain is changing due to viscosity of your sample. According to Hall pitch effect, strength of the material is dependent on grain size. So your Hall pitch equation is sigma naught plus a t to the power minus half. As your grain size is decreased, so first option is grain size increasing. So your D is increasing. So D is increasing. This thing will decrease. So this thing will also decrease. Okay. Grain size increases, length decreases. Opposite, grain size decreases, this term increases. So yeah, some of this term will increase, so sigma will increase. Length increases with decreasing the grain size. Strength is independent of grain size, it falls, and strength becomes equal to grain size. Never. Strength and grain size are completely different dimensions. Practice question, more practice questions. Mechanical mixing. Mixing at atomic level and alloy formation lead to formation of alloy in nanoscale process pi. So from mechanical mixing, you're mixing at atomic level and then you form alloy. So in mechanical alloying, you are mixing together two powders at initially it's just mechanical mixture, right? The two powders are in contact with each other. Yeah. So initially both the powders are sitting together, nothing's happening. That's your mechanical mixing. And then you have mixing at atomic level, slowly the atoms diffuse from the surface. So right after the impact, at this point, still they are sitting close to each other, but they haven't formed a perfect alloy. So due to heat, at local heating, at this point, the diffusion will start to get, and the the two material will start forming an solid state alloy. Okay. You start with mechanical mixing, and there's slow diffusion, which is mixing at atomic level, and finally you get your alloy. This happens in your mechanical line, and similarly in micro machining as well. You start with mechanical mixture, and you get your atomic level mixing, and finally alloy forming. Inert gas condensation method is generally form agglomerate film. Okay. So inert gas condensation, if you remember, you have mm, covered in last uh, here. You have your cold finger, and on top of that, your nanoparticles start to grow. And as you reach your desired length, you use a mechanical scraper to scrape off the nanoparticles. So this process leads to, since these nanoparticles are separated uh, from each other, as you scrape them, they form agglomeration-free nanoparticles. There's no thin film. The particles are sitting far apart, not coating, and it's not even bulk material. Yeah, agglomeration-free nanoparticles. My laptop. We got a power cut now. Okay. In cryomilling, leads to two major things. These are, so in cryomilling, what you're doing is cooling down your powder, which is increasing, making it more brittle. So that will increase fractures in the particle and cause deformation. It's a cryo, that means low temperature, they're not melting. Since there is no deformation, very little deformation, there's no defect or dislocation generation. It's the sample, there's no plastic deformation actually. They're breaking down into smaller particles, but there is very little dislocation generation. Okay, so only A is correct. Three important things essentially control the sintering and the spark plasma sintering process, that are current, low voltage, and Joule heating. Three things should be pressure, temperature, current and low voltage. Not really. Electron migration. Electrons are just migrating. You have very high current and local spark, creation of local spark, like plasma due to sparking. that breaks down the oxide layer between the neighboring nanoparticles, and finally atomic migration happening due to diffusion. And this is the most appropriate answer. In micro machining technique, resolution of the machining depends upon so if smaller the beam size, time of exposure doesn't really affect your resolution. How thin your beam is. The laser is the widest beam, really hard to control. You can use lenses and all, but even at high energy laser light, it's difficult to focus them onto a single spot. And again, maintaining your sample. Suppose you fix the top surface of the sample at the point where the laser focuses to a point. As soon as that point it is melted and evaporated, the point below it won't be in focus anymore, right? That will be wider than the on what will you get on the top. So it's very difficult to control it. You get a parallel beam. Even if you have parallel beam, it's difficult to focus it on electron beam. You can use electromagnets. You get much tighter beam. However, since electron have low mass, the electrostatic repulsion will uh, increase the beam diameter. In iron, since they are heavy, they can impart large energy to the surface. Due to the large mass, uh, the beam remains much more precise and sharp and thin, so you can get much better. So beam size is a factor. Beam source does play a role, but yeah, iron beam, even iron beam, you can have different sizes. Resolution is the most. In focused iron beam technique, the incident beam ions, so you have positive ions like gallium ion. Template are used for the template. Here you have your punch on the top, which has some features in it, and you just press it on a surface, and you can get indentations on the surface, which can be in nanometer range. So you straight away get nanomaterial on the top. In stress strain plot, strain hardening region is basically so strain hardening only happens in plastic region. You saw in the plastic region, you get the strain hardening coefficient N. Strain hardening happens due to pileup of dislocation. Initially, there are very little dislocations in the in your grains. But as you increase the stress beyond, uh, as you reach the yield point, what will happen? So till yield point y, initially there are very few dislocations. As you increase the stress, there will be more dislocations. At the point of yield strength, you have your maximum dislocation concentration. There's lots of dislocation piled up inside the grain. As soon as you reach across this elastic region, across the yield point, at that point, these dislocations are able to jump from one grain to other. These are able to jump from one grain to other. So that's the thing. And that's it. In the stress strain curve, what happens at the point of maximum load? So if you see at point of maximum load, your strain and stress strain plot flow becomes zero. Compressive forces become maximum. Plastic deformation happens. I think all of them should be true. Because in this region, there is plastic deformation happening. If you are talking specifically about this point, although all of them is happening, slope becomes zero. Indicate have used, but yeah, if they're talking about, I don't know, they're talking about tensile or compressive. In compressive, that will be the point of maximum compressive force. But this result will be true. I think all of this elastic region is governed by elastic region is governed by Hooke's law. S is equal to strain, A times strain, A is your Main's modulus, A or Y. Application, effect generation. Yeah, different effects start getting generated and they start moving across the grain. Generation of viscoelastic behavior now. We'll discuss the assignment first. Practice questions if we have some time left. State whether the statement is true or false. Melting temperature for bulk material is lower than nanomaterial. If you remember this equation, T is equals to TE 1 minus gamma VB by R, as R is bulk material. So bulk to P. In nanomaterial, R will be small. R is small. This entire thing will be large. 1 minus, it will be 1 minus something. So definitely it will be less than 1. This entire thing. TE multiplied with something less than 1 will point to 9. temperature, melting temperature for nanomaterial is for nanomaterial, it is lower than bulk, not the other way. For bulk material, it should be higher than nanomaterial. Gives free energy for bulk as contributions due to this is your bulk gives free energy that has on these terms. So your omega has your bond strength between the bond characteristics, correct? Mechanical mixture. So this is due to just mechanical mixture. Gives free energy due to mechanical mixture. Chemical mixing changes your gives free energy. And this Allen term, this is due to according to the Boltzmann law, is there increase in entropy due to mixing. There is an entropy due to sensory formation. What is the expression for gives change in gives free energy for pure bulk material? Again, the same equation, but for pure bulk, since mm, this is for the bulk material, right? So for pure one, you don't have different material. Ni mu I will be, there's no I is one. So this term doesn't exist. So that's why only PdP SDT term. Yeah. Mu I is for different components. So you have two component, it will be mu1 and 1, Dn1 plus mu2, Dn2. N minus. What is basically meant by nano is bulk nano crystal material. Is basically bulk material having few nano crystal grains. Really bulk, almost all of the crystal size falls inside the nanometer range. The few word is the problem here. It's basically a three-dimensional solid. Yeah, since it's bulk, it's three-dimensional. It is different from conventional large grain material due to large volume fractions of grain boundary. So since you have lots of uh, crystallites in nanometer range, there will be a lot of grain boundaries. So yeah, for large volume fraction of grain boundaries and it's basically a solid having average crystal. Yeah, average crystal size falls inside the nanometer range. If you have only few grains in nano crystal region, your average grain size will be very large, beyond maybe inside microns or something like that. Definitely more than nanometer range. Very 3D effect. Solid solution formation leads to. Okay, so this is your solid. A solid solution is increasing the entropy of the system. Your RT, LN, RTXA, LNXA. You are there are more configurations possible in mixture solid state solution. So entropy of the system is increasing. This is automatically incorrect. Gas-free energy will decrease and ideally, yeah, formation of solid solution will lead to release of energy. So H minus Ds. Their entropy is increasing. Even this term should increase. Oh, sorry, their entropy is increasing. So delta G should decrease. Surface or interfacial energy density of nanomaterial varies as function of. So if you remember this equation, the interfacial energy for nanomaterial is interfacial energy for bulk into RT ln x A concentration of bulk and your grain boundary concentration. This is your thickness of the boundary wall. Thickness of boundary wall, rho is a density, and the composition, the grain boundary. X. All three are correct. So why are grain boundaries considered? Why grains are considered as bulk in nanomaterial? So inside the grain, you can see you get perfect crystal structure, right? Their properties are same as what you get in bulk interface and all. Because all bonds are satisfied inside the grain in all directions. If you pick any atom, it has complete valency. Because because of order arrangement, because the correct option comes inside the grain as which property of nanomaterial is significant. So as you increase the grain boundaries, so suppose you have current moving from this direction, as these electrons meet these grain boundaries, they get scattered in different directions. Hmm. It lowers the electrical conductivity. Second thing is your thermal conductivity. Thermal conductivity is vibration of these lattice atoms as they pass from one grain to another. As they encounter a grain boundary, they get scattered along different directions. So, phonons, that's the combined movement of the atoms due to thermal shock. Phonons form waves, and as these phonons encounter a grain boundary, they get scattered, and that reduces your thermal conductivity. This doesn't have anything to do with grain boundaries. Surface energy, sulfur property. quantum confinement. Most correct options are yeah. Which property of nanomaterial is significantly right? For nanocrystalline material, what is the primary driving force for solid state sintering? As the nanoparticle center, one grain grows and the other grain decreases. So atoms are diffusing into this um, grain, portioning the grain, becoming the one grain becomes larger and the grains disappear. Yeah. That is to reduce the excess energy associated with the grain boundary. So grain boundary, as you know, are high energy sites. The primary reason is the reduction in excess energy associated with grain boundaries. Volume of grains fraction is decreasing. Yes, with sintering, the volume fraction of grain is decreasing. Decreasing grain boundary area. This is again decreasing as you're sintering grain boundary area. Decrease in surface energy between grain. Surface energy remains the same. It's just the total surface area is decreasing. Total surface, the total number of grain boundaries are the area of this grain boundaries is correct. Binary phase diagram. How the melting temperature of compound material and eutectic temperature. Oh yeah, we've already seen. Uh, your eutectic temperature, melting temperature, melting point. Okay, melting point is the difference between at the is the boundary between the liquid and your solid plus liquid phase, right? As you're decreasing the particle size, you're decreasing the melting point, as well as your eutectic temperature. That's also decreasing. This is the eutectic temperature, where liquid goes straight into solid phase. To this point, this is solid, liquid, liquid plus solid. This is also liquid, where liquid transforms directly into solid. Liquid. That also is decreasing. Both of them are decreasing. We can cover few. Viscoelastic behavior is mostly found in polymers because there you have these polymeric chains which can slide past each other. As you're applying stress on the sample, all these polymeric chains are being weakly bonded to each other, and over time they slip past each other. And even if you're maintaining the stress, they slowly the length increases, length is increasing. Only happens with polymeric material, where you have chains which can weakly bonded chains which can slide past each other. Interfacial effects are usually found in they're usually found in metals because in Sides usually, like in case of already one of these ions may be sitting in the interfacial side. In metals, since they have all of them has same radius, they form all the atoms are sitting on the what you call lattice positions. Whatever the positions are in the lattice structures, for example, FCC, there are four atoms sitting on the edge, in the corners, and there is the atom sitting on the face. Since all of them have same size, you get an interstitial void of some size, and where impurity can sit. Whereas in zinc oxide or some other ceramics, usually this whatever the smaller ion is, that sits in the interstitial void, and larger one forms the lattice. It's more common in metal. So the plane and the dislocation direction. Depending. This is the dislocation line, and this is the slip plane. Where dislocation line is inside the direction, where dislocation plane is along this right. This is the plane. They are perpendicular to each other. Black, blank acts as barrier for motion of. We saw green boundaries acts as barrier for motion of dislocation. Surface. According to what we've covered in the lecture, suppose you have two microstructures of same metal. One micrograph average grain size is 20, other average grain size is 1000 nanometer. 1 micron or 1000, 50 times smaller. This one is 50 times larger. Length of material in the latter case. According to your Hall pitch equation, according to Hall pitch equation, this one has larger size. So D is larger. Since D is larger, this term will decrease and your sigma will decrease. So length will be less in case of the latter case. Okay, we're already past the time. Yeah. Thank you all for attending. I'll upload the session on YouTube. Be sure to submit your grades assignment before. The slides will be uploaded on the Google Drive. If you have any questions, you can mail them. Mail them. It's leveled out. Copy.